Hi everyone, it is day number 11 for our 30 days, 30 machine learning projects challenge. So let's solve it. It is anomaly detection in network traffic with isolation forest. We did a problem using random forest algorithm. So I guess this is going to be something similar. So let's start. Here it is day 11 and here is the problem. So this the flow is going to be same. Uh, we will be asking questions from ChatGPT. We will also ask ChatGPT to give us the code, and then uh, for every step we are going to understand and ask for explanation from ChatGPT. Uh, yes. So I'll start. So it says that great. For day 11, we will be focusing on anomaly detection in network traffic using the isolation forest algorithm. This method is ideal for detecting outliers or anomalies in large data set. Okay, anomalies as in the outliers, as in that's something different, such as network traffic, where usual patterns might indicate an attack or malfunction. Here's how we can approach the problem step by step. So first we will load the data. We can load the data. So it says that we'll start by loading a dataset which contains network traffic information. You can use a dataset from sources like Cabal or UCI machine learning repository, which contains labeled traffic data with anomalies. Anomalies. So let's start with. mm, I'll go and say network traffic Cabal. Network traffic Cabal, and let's see. Suggest me a simple data set. It is a little complex. So let's start with this. Since we are not able to get the data set for this one, let's because we have to apply the isolation forest. Maybe we can apply on something like this credit card fraud detection. And let's download the data here. Mhm. So it should have a class. Let's see if it has class. Mm, okay. Do you think I can get this set from Learn? I'm saying let's see if I can get the data from Learn. And what do we have to apply? We have to apply which type of? We have to isolation forest. Isolation forest. let's 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 do this. Here we might be able to get the data. Hmm. Okay, so they all are pointing to this problem only, and they all are solving through the isolation thing only. So yeah, let's go ahead and go ahead with this only. So I'll go and modify the title of this problem. So the title of this problem is going to be same, but we are going to get uh, find the anomaly detection with isolation forest in the credit card fraud detection dataset available on the here. Okay, so here it says, okay, time V1, V2, V3, V4, V9. So let's download this and let's go back and let it be downloaded completely. Okay, so I'm now going to go ahead with this data set uh, for this problem, and this is the data set. So let's go and read this data set. Let's clear it, close it, and then move the data set from download folder to our dataset folder, and we should see it here. And let's create a new file for today's problem. It is going to be d11.py. Okay, add it to the Git repository. Import libraries. So the before that, the is problem is going to be anomaly section, anomaly detection with isolation forest in credit card fraud detection dataset. Okay. Okay. So I'll go ahead with this one. And for that, first we have to do what we will import the pandas as PD. And step number one is going to be load the data. And here it is going to be data is going to be panda.read CSV data set credit card CSV and print the data head and clear the terminal, run this file. And this is how, okay, we do see a column called class. So, okay, okay, I am going, okay, understood. So we do see a column called class, so we can go ahead with it. So let's go and do the step number two, which is pre-process the data. Um, since our data mostly contains numerical features, they all are numerical features, there won't be a need for complex data. So we do not have to convert any textual or any non-numeric thing to a numerical thing, which machine learning algorithms usually understand. So it is not going to involve any complex pre-processing. So we will do what? We will create the feature. Um So here we will skip it and create feature and target data sets. Give me a second, let me drink water. So here it is going to be data after dropping the class after dropping the class, and we have to drop the class not row, we have to drop the class column, and the y is going to be data class, and this is going to be our feature, and this is going to be our target. One for 4 here, 0 target, 0 for normal transaction, and 1 for fraud. So let's print it x dot head, and then print y dot head. So let's clear it, the terminal, and run our program. We can see the this data is looking like this, all the V1, V2, all the transactions and the amount, and version 1, version 2. Here this is going to be a class. They all seem to be, the first five at least look like normal transaction. I just want to know what this V1, V2 are. So let's go back. Time is the number of time seconds elapsed between the transaction and the first transaction. So okay, and then V1 may be the result of the PC dimensional deduction to protect user identification and sensitive features. V2, V3, V4. Okay, something related to the user. Let's comment it and then go to step number 3, which is going to be the split. Uh, I don't see the split and the data process step. Why was it not here? Okay, you are right here. Okay, so ChatGPT missed the data split step for credit card fraud detection dataset. Okay, so we have downloaded it. Then we have created these features and separate. So let's create import the library from SQ1 to model section, import test train test split, and step 3 is going to be split the data into training and validation data sets. And here we split into 80-20 ratio. Training is going to be the 80% and validation data set is going to be 20%. So what we will do, we will create X train, X validate, Y train, Y validation, test train split, X, Y. The size for the test dataset is going to be 0.2, which is going to be the 20%. Random state is going to be 42 now, which is a random number. We use it because we want to give because we want to be sure that whenever we are running the script, we will get same split. Uh, it will create same split. as in for extreme and extra. So what we will do, we will print extreme dot shape and x validation dot shape. Let's clear the terminal and rerun this file. So the shape for this one is going to be this, and for validation data set is feature set is going to be this. Let's comment this and then go to. Okay, it says that we must use this stratify by. What is the need for this? This ensures that the class distribution for was non for remains consistent and both training. Okay, so let's do this stratify by. So class distribution for fraud and non-fraud remains same. So let's do this. Uh, let's move from here and do put it here. Okay. Now let's go because we are. This is making sure that the data is balanced. Uh, so now step number 4 is apply. Okay. Model build model and train. Build and train the model. So what we are going to do, we will use sklearn.ensemble for inputting the isolation forest from sklearn.ensemble import isolation forest, and we are going to build the model isolation forest. So let's understand this first, and then we will predict it, and then we will do what we will print this. Okay, okay. Hmm. Predict anomalies, view prediction, and then we will do evaluate the model, and then we will plot it like the usual steps. Before I build and train the model, I want to understand what about isolation forest model. Can you please explain it, what it is and how it works in easy language? So let's see. Let's first understand what this isolation forest algorithm is about. Okay. So it says that isolation forest is an algorithm specifically designed for anomaly detection. It works by isolating outliers or unusual data points in a dataset. Here's how it works in simple terms. Just like a decision tree, okay, we have worked with decision trees. Split data based on features. The isolation forest splits the data into isolate each data point. The key idea is that anomalies, unusual or abnormal points, are easier to isolate because they are significantly different from the rest of the data. Makes sense. Normal data points. They are usually close to each other, or isolating them takes more splits or steps. Anomalies. These points are far from the majority of the data, so it takes fewer splits to isolate them. Two. So what it says that in the isolation forest, if let's assume we have a data, and the data has some anomalies, as in some unusual, abnormal points, then it becomes very easier to isolate them from the majority of the data. So that is why that is how it works. And to understand how it works, the algorithm, random splitting. There are three things. Random splitting. The algorithm selects a random feature and then randomly chooses a value between the minimum and the maximum value of that feature. This process is repeated until the data is split onto individual points. Okay. So it is going to pick up a random feature and from minimum to maximum value it is going to split. Okay, where it stays. Then, if a data point is easily isolated with very few splits, it is likely an normal. Okay, with very few splits, if it is going to be isolated, it is a norm. It is anomaly. And normal data point being grouped together require more split to isolate. Okay. Uh, Averages. The algorithm builds multiple isolation trees to average out the split required to isolate a point. The fewer the splits required, the more likely to the point is to be classified as the anomaly. So, so why is it called? So what it does, splits as in it takes multiple iteration to split the data from the majority of the data. If it is going to take fewer splits, iterations, then most likely it is an anomaly. And if it is going to be going to take more splits, then it is tightly grouped with the similar data points. So it is not going to be an anomaly. Let's visualize it. Let me isolation forest looks like. Okay, this is how it looks like. Anomaly, anomaly, anomaly. This is not. This is not an anomaly. Okay. Why is it called isolation forest? The term isolation forest comes from the fact that it is based on decision trees, okay, which are used to split or isolate data. Like a forest or trees, it builds multiple trees to get better average of how isolated a point is. Okay, it builds multiple trees. Key benefits of isolation forest: efficiency. It is very fast compared to other anomaly detection method because it does not require distance calculation between all data points. Okay, it is fast because it does not require distance calculation between all data points because it takes splits by creating the trees. Scalability. It can handle large data sets, making it useful for high dimensional data like network traffic or credit card transaction. Okay. How it helps with anomaly detection. When used in anomaly detection, isolation forest builds multiple trees. Okay. Each randomly splitting the data creates the average path length. That is how many splits it took to isolate each point. If a point has a shorter path length, it is likely to be an anomaly. If the point requires more split, as in the path length of the tree for from reaching from the root to that particular point, like, like from reaching from the root to the particular point, is the path is large, then it is not an anomaly. If the path is smaller, then it is going to be an anomaly. Like this red point here, anomaly. Okay, and it does this on multiple features. So yes, in a sense, and then it what it does it implements an average, and by calculating the average of after applying on all the features, it gets whether the particular data is an anomaly or not. In essence, isolation follows isolates anomalies because they stand out from the rest of the data, making them easily understood. Understand. So what it does, it is like an extension of the decision tree, where it creates multiple trees, okay, or forests, and each tree is created from a feature, and it picks up a feature and then it divides the data. And if the data point gets divided quickly by calculating the distance from the root to the respective point, then that point is going to be an anomaly because it it gets split, it gets isolated very quickly, so it is an outlier, uh, or an abnormal data. If it takes multiple iteration, if the length between the root and the point, respective point is large, then it is not an anomaly. Okay, understand. So let's implement it. Here we are doing this. If we go back and understand this, here what we are doing, we are contamination. Here, okay, I understand. So can you please explain the parameters passed here? So I want to understand why we are passing this contamination law and random state. In the model isolation forest, the contamination is 0.01. Random state is 42. Two key parameters have been passed to the isolation forest model: contamination and random state. Contamination refers to the proportion of anomalies that are classed in a dataset. Essentially, it is expected fraction of the dataset that is considered to be anomalous. In this case, 0.01 means that the model expects that 0.1%, that is 1 out of 100,000 data points in the datasets are anomalous. So we have to, I guess, make an assumption here. Why it matters? The contamination in this contamination parameter helps the model determine the decision boundary between normal and anomalous point. If you get higher contamination value, the model will classify more points than normal. Okay, understood. So we can take it as the distance. If we keep the distance higher, okay. So for example, distance is 5. This is the distance 5, and this is also 5. So these two are anomalies. Mm, set height, the model will classify more points as anomalies. Okay, so it says that it is common to experiment with different values. So we will experiment with different values. As in, contamination parameter is that how much anomalies we expect. Okay, randomness is the randomness of the model. It ensures that if you run the algorithm multiple times with the same data, you get the same result each time. Okay, so let's go, and here what we are going to do, I want to be sure that I do mention what is a contamination and what is uh, random state. So the contamination is going to be 0.01. What we are doing with the contamination is that we assume that the anomalies are rare here, and if we pass higher value here, we assume that more points are going to be anomalies. Then yeah, more points are going to be anomalies, uh, which means we say that we assume 100. Let's say with this we say that 1 out of 1,000 is are anomalies. We then if we pass this value as something higher, we'll say that we expect 200 points as anomalies. So that rare uniqueness decreases. So yes, the isolation quotient decreases. So that is why we will experiment it with it by after completing the code. So the random state we pass because we want to make sure that if we run this code multiple times, uh, the algorithm on the same data, we get the same data. And 42, as I've told you, with this test script, it is a random number. Um, See, it has no special mathematical meaning but ensures reproducibility. Okay. Once done, what we are going to do, we'll go back to the code, and here what we are doing, we will fit it. We will go back and we will fit them. We will train the model. So model is going to be trained on X train. Okay. Predict anomalies on test data. So what we are going to do, predict and predict and anomalies on test data. And what we are going to do, uh, that is minus 1 is means anomaly and 1 means normal transaction. Yeah, normal. And let's do this. And did you, I want to see. Okay. Hmm. So we will do what? We will predict this. Predictions are going to be modeled on predict on what x train. If for x validation it should be. Let's see what it will do on the here. Yes, x prediction. And then what we are going to do data set, what we are going to create a data frame of this prediction. Print uh, okay, we are creating a data set out of x test. Okay, let's understand why we are doing. And I guess that was itself a data set, right? X, I would have done this also, no? X anomaly. I don't have to do that right here. And what we are going to do? Predictions. Let's print this x, hang on, x validation, x validation. Let's print this. Run this code again. Okay, so on validation we are predicting, making the prediction, and for everything it says it is an anomaly. I'm a little confused on why we are doing this. I am. Can you help me with step 4 and step 5 after uh, adding the split step? Adding the split step. So here the step is build and train the isolation model, and it is going to be again same thing. That's what we have done, right? We trained the model on extreme, then we predicted on the test set which is x test, and on the x test itself. See, I was right. X validation, I have to add a column called anomaly and pass these test predictions. Okay, and the isolation forest model is trained on the training data. Okay, we use train model to predict anomalies on the test data. Predictions will be -1 for anomalies, normal points. Okay, for normal, these are normal. -1 is going to be an anomaly. Okay, and now we are going to be on the step number 5. Step 5 is evaluate and visualize. Ideally, step 5 should be that. Step 5 should be evaluate, make predictions and evaluate. So it is going to be this, and evaluate will be what? I don't think we need confusion matrix and classification here. But yeah, let's see. I want to see this this that we were earlier seeing, something like this. So we do not delete the x and y here. Okay, in data itself we are adding the predictions. Oh, that is a really good step. Instead of going ahead with this way that we usually do, uh, let's go ahead with this way and then we'll go how many predictions we have made. From sk1 dot matrix import accuracy score classification. I want to know, do we need confusion matrix as it is? Okay, no, we do need, because we are classifying from a fraud and normal and non-normal transaction, right? So confusion matrix and classification report, and then we are going to go back here. Here what we'll go accuracy score is going to be between the validation data and the predictions data has moved. So actually one and the predictions. So now we'll print the accuracy score going to be accuracy score. Let's print the confusion matrix and then we will run it all together between the actual values and the predictions made. Print, let's copy print here confusion matrix, and then classification mode is going to be between the actual values and the predicted values, and then we are going to print again here, and it is going to be classification report classification report. Let's run it and see how well the model is performing. Okay, we are getting the error like this. I'm getting the error like that. And I want to see what here it was doing. Here, if you see, it was adding this anomaly of predictions in the uh, data itself. Okay, uh, and then it was checking how many of the data was anomalies detected, and then was printing. It was actually better. So we can, in classification report we can do this. We got this earlier also, when the it says when the sets the precision of school consider in case no positive predictions are made. Okay, when the class, when for particular class, let's okay, Why does it happen when the model does not predict any data points belonging to one of the class? The precision or F score become unidentified for that class. This can occur if the data is highly imbalanced and majority of the class dominates and the model fails to detect. Okay, when the data is highly imbalanced, that is, majority of the class fails to detect anomalies. Model fails to detect anomalies for a particular case. So what we can do, we can comment it for now and explore the or explore rerun it. Okay, now it works. So here we can see. Okay. Um, okay. Let me copy it and I'm a little confused as well. From matplot.py as import as PLT, and let's see. Step number 6 is visualize. So visualization. That's it is going to be well predictions. Okay, let's run it and see what it is going to do. Because I'm still a little cooler on on version 1 and V2 on two transactions only. This is how it is looking. There are many, most of the ones are red ones are anomalies, so it has a lot of anomalies. And I'm not happy with how it is looking. Let's comment it. And I want to experiment with this, how we were doing it here. Uh, I want to evaluate like this. So let's see if we want to calculate how many of them are, how many fraud cases were detected. Uh, then we can do that by, okay, and we can do that. Okay, I'm understood. And or we can do this also. In the anomalies, many true fraud cases were detected. Calculate how many true fraud cases were detected. So we need anomalies detected. Anomalies detected is going to be between X validation, which is going to be the actual value. Here we will take only the ones whose Y value is 1, which is okay, which is a normal transaction. If we remember, it is a fraud, and the predicted prediction is so okay. We have added in this one, right? And here anomaly is also 1. It was a fraud and it is a fraud. Both are fraud. So which means anomalies detected correctly was okay. So the predicted anomalies are this, and they were originally were anomalies. So we are going to get that. Okay, it's minus 1 G means anomalies, right? So we will print that. Print It is number of anomalies detected is going to be length of anomalies detected. Let's run it and see it. So 65 total anomalies detected. See, it is same in the conclusion matrix. Uh, and then, okay, if I want to calculate how many fraud were detected. Calculate how many fraud were detected. Frauds will be fraud cases were fraud cases were were missed. So they were fraud. Now they are predicted normally. Fraud. So it is going to be fraud. Missed is going to be X in the actual code. Calculate the they were fraud. Okay. Now in the anomalies they are they are not fraud. So we are going to do number of fraud missed is going to be total number of fraud missed. So it is going to be less than those they were fraud in the original data, but they are normal in the predicted data. And see, it is 33. Okay. Now calculate how many normal transactions were normally classified as not. Calculate how many normal transactions are predicted as anomalies. So it is going to be false positive. We have predicted them as anomalies, so they are positive, but they are mispredicted, so false. So it is going to be x value. They were uh, originally they were normal transactions. Now in the uh, prediction, they are predicted as uh, anomaly. So print number of false positive is going to be, so let's rerun it and see. It is 553. Okay, see. Okay, so do you see some number? It makes sense now. So what we did today, let me do this, and let me put a uh, heat map also. Import cbond as SNS, and here we are plotting a graph between the version 1 and version 2 of the original, sorry, predicted values, and we are printing the predictions. And here I want to do what? Here I'll copy it. I'll create a C1. It is going to be same size. It is going to be SNS as heat, heat map confusion matrix. Annotation, yes. Format is going to be numeric, and the X ticker is going to be. mm, I want to wish, see the confusion matrix. Heat Now, so what it going to see, what it will show. Hmm. Now, okay, I missed one thing. The color. Color is going to be blues, and it is going to be the X state label are going to be normal and anomaly. So it is going to be X is normal and it is anomaly, and Y tech labels are going to be the actual values. Um, Actual or true normal. True normal, and it is going to be true anomaly. On Y side we have the true values, original values. On the left side we have the predicted values. And in the now we have um, predicted, and we have true, or what we can say actual. Uh, we'll say confusion matrix here. Confusion matrix here, and I don't want legend here. So let's gain our net. So this is how the isolation forest between anomalies and normal transactions are looking like. And this is how confusion matrix is looking like. So if we see, yes, I want to see why the confusion matrix has three data. Uh, why the confusion matrix has three columns here. The confusion matrix having three columns likely indicates that one of the labels used in the prediction does not match expected binary classification labels. Typically, in normal detection, we expect two labels, 0 and -1. If you're seeing three columns, it means that the third expected value is hidden. Okay, maybe because uh, the y text should have done 0 1. The y text should return minus and 1. If you find a third table that is not expected, you need to clean the data to ensure only valid labels. Y text. Mm, let's do this. In the now I'm understanding why is it like why we have three columns. It should be two columns only, right? So let's print. Let's comment this. Comment this. Let's print X test validation and maybe unique. So let's do this. So normally are two only. Okay, and if I do y, uh, which is the validation target values, the true values, It is 0 1. So this is, it says unique value is the same only, right? Um, confusion matrix. Okay, so again, see what this is what we have to do. Predictions, predictions. Predictions. I want to print the predictions here. So predictions are going to be this. Predictions is like this. Check that code. I'm asking ChatGPT only, but there are a couple of important need to address the three column matrix and should ensure it works as binary classification fraud and non-fraud. Okay. So what we are doing here, this is going to predict between -1 and normally into 0. So here what we can do, here the confirm we are getting as 3 column because the predicted values are -1 for normally is 1 for the normal has 0 and next one labels is calling the confusion to the confusion matrix. Map your Y level to match the prediction from the isolation. So both sets are okay. So if I go here, what I can do, the Y becomes Y dot map Y dot. If I do this map, the 0 maps to 1, 1 maps to 1. Let's rerun it and see if it will work because we are splitting Y into Y validation and Y train, right? Okay. Or what if, so I suppose I want to see what the data has. Let me go to the credit card score and let's see if it has any uh, Y. False positive. Let's see. And here, if we do that, For calculating the confusion matrix, let's do this. And let's calculate this. Hmm. Now the data looks better. Okay. So we have to go ahead with that only, keeping the mapping here because it works on 0 and 1. I want to ask this. Why are we even keeping 0 and 1 as keeping target? Why can't we map 0 to 1 and 1 to -1 in start only? Does isolation forest will, will, will create any problem? So we are doing it later. Maybe because isolation works on 0 and 1, but isolation predicts in -1 and 1. And because of that, it is creating problem with accuracy and everything. So here also what we can do. So it says it is a valid question. Yes, it is possible to map the target value 0 for normal and 1 for fog to match the labels expected by the forest isolation. That is 1 for normal, minus 1. Here's an explanation why and when it might matter. Why use original target mapping 0 and 1 for fog? Supervised learning context, consistency across model. From 0 to 1 instant. If you map the values at start, it won't necessarily cause problem for isolation problem because isolation problem is an unsupervised learning. Use the target labels using training. Just the feature matter. Okay, it does not use the target labels for training. It isolates anomalies by constructing random decision trees determining how distant or isolated each point is. It does not need label like 1 or -1 during the training but uses contamination parameters to identify certain proportion of. Okay. Before training evaluation can be helpful for evaluation consistent but won't affect the training process. No. Okay, won't create any problem. Why? Because it focuses on the feature classification, not on the label, and it can actually simplify the process when using model for anomaly detection. Since isolation forest does not use the targets labels during. Yes, yes, correct. Instead of that, let's convert this only, and let's rerun it. And I want to see how many. Okay, perfect. Now I want to see how many. I want to see how many uh, values in y r z y 1 and how r minus 1. How many r minus 1? So we can do that. Okay. Check the distribution of values in y after mapping. So value counts. We can print the value counts. So we can do that with print y, hang on, counts. I've printed it. Let's run the program again. Let's, let's go back. So, and 0 to 1, 1 to minus 1. That is why it is great. That is why. I was seeing that it has only one class. Yes. Now it looks better. Now it looks better. Yes. Yes. Now we are talking. So initially only we have mapped 0 to 1 and 1 to minus 1. Now later we do not have to do anything, right? The unique values are also coming, right? So let's now see the plot, run the code, and this is how the anomalies and normal transactions in a scattered graph is looking, and this is how our confusion matrix is looking. Predicted anomalies correctly are 307, and correctly predicted normal values are uh, 53. uh, false 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 positives are 45, as in they are predicted anomalies but they were not 45, and the ones which are predicted normal but actually they were anomaly, so the frauds that we have missed are 557. uh, so 557s are anomalies detected. Okay, so we may have to correct this also. um, Anomalies detected, it is going to be, let me corrected, minus 1 as anomaly, change for consistency. So it is going to be minus 1 for anomalies. So let's change it here. Minus 1 for anomalies and 1 for here. We want to detect anomalies detected. So minus 1 and minus 1. Originally they were minus 1, now also minus 1. Fraud missed. Originally they were minus 1, now they are not. They are normal. False positive, as in originally they were uh, 0 is minus 1, they were like normal. uh, 1, 1, 1, 1. Originally they were like normal transactions, and we are saying that they are anomalies, so they are false positives. So let's run it. Okay, now it is coming correct. Okay, I did not close the last one. For script. Let me come back to, let's run again. Scattered graph, anomalies, and number of anomalies detected 53, 53. Number of anomalies fraud missed 45. Correct. So they were coming as, yes. Number of false positives, this. Let's come back. Normal. 1 means normal, minus 1 is anomalies. They were anomalies, now anomalies. So number of anomalies detected are 53. Let's rerun it. So number of anomalies detected are, so it is going to be minus 1, 1. Normal anomaly. Normal anomaly. Normal is 53, 45, 57, 55, 60. Correct. So it is second column is anomaly. So second is anomaly. So it is 1 minus 1. It should be ulta. Should be ulta, no? It is correct actually. So anomalies detected are going to be in the original one they are minus 1. In anomalies also they are minus 1. Anomalies. So it is going to be number of anomalies detected 1. Let's run it as 1 1 x. Let's run it 1 1. Yes, correct. So 1 and 1 they were normal. For 0 it is mm, not. 1 is minus 1. 1 means fraud. So for fraud it is converted into minus 1. The fraud is converted into minus 1. Uh, Let me ask ChatGPT only. Can we calculate this? Hmm. Slight adjustment, right? So anomalies number of fraud case detected are this. Number of fraud cases missed are minus 1 1. A number of false positives are 1 minus 1. And this is my confusion matrix. I guess the labels are not right. Uh, is it? Okay, yes, confusion are reversed based on the matrix value. Correct, yes, exactly. So it should be minus 1 first, and then it should be 1, and then it should be 1. It should be minus 1 first, and then it should be 1. New line. Okay, let's run it and then see scattered graph. Okay, so the normal ones are detected as the true positives are so normally is detected 557. The normal transactions are this. Uh, True and normal detected 53. True normal ones are detected this. False positives are which are normally now and they were normal, which is like false positive 557. They are normal. They are detected as they were anomalies. So fraud miss 45. Fraud miss 45. Anomalies detected are 53, and the number of false positive, as in they are anomaly but they were normal, are 557. Correct. So yes, this is how the program is looking like. What we have learned today is we have used isolation forest model. Why? Because it helps in it works. It creates multiple trees like decision tree, and yes, And what it does, if we go uh, yeah here, what it does, it performs multiple iterations, and on those iterations, if what it does, it tries to isolate a point. If the point gets isolated quickly, it is an anomaly, otherwise it is not. Then we had calculated, yeah, we calculated the confusion matrix, and then in normal terms, we uh, found out the number of anomalies detected, fraud missed, and false positive. This is exactly similar that we can see in the confusion matrix. And then we drew scattered graph and the heat map of the confusion matrix. Also, what we did, we added the anomaly as a new column to our original data. So yes, this looks fine. The accuracy is coming as 98%. So it is looking good. So let's add this to our um, Git repository. Add code for D11 and then push to main. Let's go back and see how it looks, and we can see the data for our day 11. Yes, so today was a challenging, but we have learned a lot. Yes, see, bottom right, the two normals predicted as normals are 56307. Correct. So thank you very much. Hopefully, we will solve more problem, and in future we will understand more about it by building complex projects. Thank you very much.